So yeah, my name is Mario Almeida. I'll be giving a practical guide on scaling federated learning on distributed hardware. So Stefano's already introduced myself, but basically in the past I've been stuck in between research and industry. I've done research at Telefonica and at Samsung, and in the meanwhile, in between, I've done a lot of different startups, some of them my own. And I've also studied in more universities than I actually have degrees from. I did distributed systems, Erasmus Mundus, and the PhD in UPC. So in this talk, I'm going to be first discussing a bit about the differences between simulation and real world experiments. Then this talk will be a bit on the practical guidelines for federated learning simulation, but also to perform federated learning on mobile and embedded devices. And in every of these topics, I'll be trying to focus a bit on scaling as well in terms of clients and devices. So the first part, let's look at what we generally consider simulation environment for federated learning. Typically, if you're doing federated learning, either it be on your local machine, on your university cluster, or over the cloud, you typically have pretty good stable network connection, often gigabit connection even. You have low communication overhead. You also have a lot of GPUs available, typically a lot of resources. And for federated learning simulations, people tend to resort to often synthetic data sets that try to mimic the real world. On the other hand, on the real world, you have things like heterogeneous devices with very different hardware capabilities. So for example, in CPUs, you have different architectures with different cores, different frequencies, different energy requirements, but also you have other things like memory, the presence or not of a GPU, but other things like battery capacity and so on. On the other hand as well, devices in the wild, like mobile phones, tend to be quite slow at running machine learning models. So here you see an example of the latency that you achieve for various very well-known deep neural network models over a GPU in the left, a desktop GPU. And on the right, in the mobile CPU, I believe this CPU was back then from the S9. And you can see that the same model can take up to 2 orders of magnitude more time to actually perform inference. Another thing about devices in the wild is that these can have multiple different states and availability. You can have devices that go out of power, they can be idle, the screen can go off on Android devices and on OS Apple devices as well, and these tend to kill all the background applications. You can have power saving mode that typically does a bit of frequency scaling and does your code might run a bit slower, or the devices can be charging, so they have like the full power to kind of push the performance envelope. Furthermore, in the real world, you might actually have very distinct data distributions and demographics. So for example, if you are expecting to do a classifier on simple things, like what you would consider a bed might be very different. The concept of a bed might be very different in France versus like a country like Somalia. And here I would like to point to this website, Dollar Street. It's a very interesting source of this kind of discrepancies. Furthermore, when you're executing on a mobile device, you also need to contend for resources with other applications, right? So your user might be using YouTube to see 4K videos. They might be using Snapchat with some filters on image. They might even be mining cryptocurrencies. Who knows nowadays, right? So your TensorFlow models might be fighting for resources with all these different third parties. In terms of data, it's also often the case that mobile devices will have very small data sets. And these data sets sometimes can even be very monotonous in terms of the variation of data that you see. It can be photos from the same cat from different angles or something like this. And finally, since you have millions of devices, it is often the case that you visit a device only once, further raising the importance of including every single device so that you have models that kind of have visibility over the whole distribution. So let's go into federated simulation. The very first step on federated simulation is picking the right proxy data, okay? And here, to give an example, imagine that you are building a dog classifier, a simple classifier, binary classifier that simply says if something is a dog or not. And if you train it over a data set that has the dogs that you see here in an image, if then suddenly you go and try to execute your model in Asia and you see a dog like this, obviously your model is going to fail. So the very first rule is that your distribution of samples should mimic the real world setup. Another thing is that imagine that you're training a speech model, for example, and you train it with a simple one-word sentences. If then you go into the real world and suddenly you have very long sentences, you will have bad performance as well. So another thing is that you should be trying to match the data properties. So in the case of language models, the sentence length should be representative as well. Another thing about data is that it can change over time. So if you are studying something like a language and language within some communities, for example, like Fortran changes frequently because new words are added all the time, then it might be hard for you to keep track with the evolution of your data. So in practice, how it works is that the models that you are putting out through simulation, you need to test them in production very often until the real world performance comes closer to your simulation. So let's dive a bit into scaling to hundreds of clients in federated simulation. So typically when you want to run your deep neural networks on your local resources, on your CPU and GPU, here on the left and right respectively, typically your model or your, in this case, federated learning client can be, for example, a Flower client, like we've seen in Steph's presentation. You would basically have resources on the CPU and resources on the GPU that you need to allocate. Now, in a federated learning round, you actually have several clients. So when you're trying to simulate all of these clients, if you don't want them to run in sequence, you need to somehow parallelize these on your resources. And so far, so well, this is quite a simple scenario just with a CPU and a GPU. But when you start going into clusters, you will start having to distribute your clients through many nodes. And here we're giving an example. The yellow boxes are a client. We are assuming here that the client takes 5 gigabytes of GPU memory. And the reason why we're focusing here on GPU memory is because when you're dealing with clusters, typically CPU resources, RAM resources, storage resources are quite common and you can scale them very easily, but the GPUs can be harder to scale, okay? So typically these systems are memory bound, and often the way that you maximize your use of your resources is by trying to see what is the budget of GPU memory that you have, how much each client takes, and try to maximize the number of clients that you run on your platform. Now the question comes, how do you scale to the thousands of clients, right? You only have these limited resources. In this case, we're showing an example with just 20 clients, okay? How do you scale to, in this case, 200 clients? So one of the main takeaways here is that you don't need to run all the clients at the same time. Let me just have a drink. Hopefully you already found Wally. So you don't need to run all the clients at the same time. In practice, as Stefanos already referenced, you can sample the clients for each round, right? So in this example, we have 20 clients, but typically you don't run more than 3 clients at a time if you sample only 50% of the clients that you have, right? So basically in the first round, you can have something like client 4, 10, and 11 executing. And on the second round, client 7, 12, and 17. But the thing is, in most machine learning frameworks that you have nowadays, they do a very good job at allocating memory in the GPUs to execute your machine learning models, but there aren't that many functionality when it comes to managing this memory. So it's quite challenging to release, for example, the memory that you allocate on GPU without resorting to things like killing the process that allocated the memory in the first place. So one very cool trick that you can do in order to scale to the thousands of clients is to use pseudo clients. Okay, so the idea with pseudo clients is that instead of the normal workflow that you see in many federated learning frameworks, in which each of the clients knows, each client knows its ID, and the server basically just samples a subset of the IDs and then contacts directly these instances, these clients. In this case, the server communicates as well the client ID. And how this works is that basically you can emulate several clients over a reduced number of pseudo clients. So in this case, we have only 4 clients, but we are doing a modulo of these clients, so that, for example, in the first round, you can have the first client representing the first pseudo client representing client 4, and on the second round, having him represent, for example, the client ID 12. So it's this idea of a client receiving a client ID, a pseudo client receiving a client ID, and going into the data set and fetching only the subset that should represent the original client ID data set. So that's the idea. Now, you still need at least as many clients as a server can sample per round, okay? So basically, in this case, we had only 3 clients that need to run per round, and we had 4 pseudo clients, so this is fine. But if you need to run more clients than you have pseudo clients still, then you would need to resort to running things sequentially, so you could potentially put a queue on the clients before execute. Finally, you can have all of these clients, but how do you actually deploy and orchestrate them over large clusters? So there are many paths towards scaling federated learning. In these examples, we will focus primarily on Docker, on setups that use Docker. And the main reason here is because most of the federated learning frameworks already provide pre-configured Docker instances. So if you've been living under a rock and you don't know what Docker is, it is similar to the concept of virtual machines, in which you virtualize an operating system and run your application there. And the idea here is to have a configuration that you can basically migrate to another machine, and it just works the same way with the same dependencies. Instead of doing it like in a virtual machine that virtualizes the whole operating system and kernel, basically containers, what they do is that they share the kernel with the host machine, and your applications run basically as applications in the host, but in an isolated manner. Now, running PyTorch, for example, within a container, it's quite simple. It's basically a one-liner, assuming that you already pre-installed Docker. So if you run this, it will fetch the image and it will execute locally, and you will have an instance that you can SSH and run your PyTorch scripts. Now, you can have a Docker instance, and you want to deploy your Docker, you want to deploy your Docker image across hundreds of machines, and this can be quite challenging to do by hand, obviously. You can use configuration tools like Ansible or Salt to kind of automate this configuration across multiple nodes. But the de facto standard for orchestration of Kubernetes, of Docker, it's basically the use of Kubernetes. And I'm not going to go into too much detail into Kubernetes, but the main idea here is that each node has a controller. This controller is able to launch your Docker instances on these various nodes. Each node as well runs a kind of a kube proxy that allows you to have over your whole cluster a kind of a network mesh that allows you to perform service discovery and find any service by name. Okay. So the cool thing about Kubernetes is that once you have a cluster deployed, you can use the Kubernetes client, which they call kubectl, to deploy your Docker instances over any platform that you might want. So if you deploy it locally through pure Kubernetes, or if you are using an unmanaged service in the cloud, like AKS or EKS, in all the major clouds, you can find a representative of Kubernetes. It just works with the similar clients. Then you have other open source projects that work on top of Kubernetes that allow you to have like a very broad environment when it comes to machine learning. So if you have more advanced needs, you can actually use something like Kubeflow, and Kubeflow provides you all the tooling that you might need for machine learning, from things like Jupyter notebooks to kind of monitoring databases like Prometheus, all the way to things to do serving of APIs and the ability to host over, again, through Kubernetes on the most popular cloud infrastructures. Now, the thing with Kubeflow and with Docker, as a matter of fact, is that you typically configure things through YAML files. And many of us might not like doing things like this. So for the people that don't really like these YAML files, there are several tools that you can use to kind of scale your machine learning experiments. I'm not going to go through all of them, but typically these are grouped into two kind of tools. For example, some of them run on top of Kubeflow. And in this example, for example, you do your code in a notebook, and your code automatically translates to tasks to run on Kubeflow, and they get parallelized automatically. On the other hand, you have other kind of tools that work more on a task basis. So in the sense that you can implement a task to execute, and this task could be a fit round, or could be like some iterations on the client or something like this. And you can define also the resources that are allocated per task. So you can use these tools to kind of scale as well your experiments for federated learning, but you also have a bit of effort of integrating this into the existing frameworks. So now let's look at a different scenario. So we're moving out from the simulation, and we're going to look more into federated learning on mobile and embedded devices. So first, we'll focus on how to run on mobile and embedded devices. So if you're considering things like IoT devices, like Raspberry Pis or the very popular NVIDIA Jetson, as we mentioned before, most FL frameworks already provide pre-configured Docker containers. So it's very easy to launch this on different hardware, because typically it's quite challenging to compile these frameworks for some of these platforms. Another very interesting property of these devices is that if you execute for too long, you are very likely to reach issues, or to start having issues with eating. And when a device overeats, typically the frequency of your processor is going to decrease, and you're going to be affected in terms of performance. But this frequency scaling is also a very good opportunity for you to reduce the frequency of your CPU, or your power, the frequency of your CPU, and at the same time consume less power, so that you can execute machine learning models for longer. Now, training on mobile devices is not as easy as it seems. Until very recently, there weren't that many libraries that enabled training on device. So one that has been there for quite a long time is deep learning for Java, but it is extremely slow to perform training on device. A bit more recently, you had TF-Lite personalization and transfer learning. We will see in the next slide how more or less this works. And very recently, TF-Lite actually introduced on-device training, okay? So the example of the transfer learning, which is the one that has the most documentation right now, typically you, on your desktop, for example, you train the model, then you basically, you put the model through the TF-Lite converter, you convert it to a TF-Lite model, deploy it on the mobile phone, and then on the mobile phone, you will have the TF-Lite interpreter, which can be, you can be interacting with it through a Java layer or through C++, and it executes on the local hardware. Here on top, you have a base model and an head model. Again, this is representing the case in which you are doing transfer learning. So the base model can be the full model, while the head might be pointing at a different further down or further up the network. So finally, how do you scale to millions of devices? So here the setup is quite different from simulation, okay? First, it's that in simulation, you might be dealing with thousands of clients. You can also go to millions of clients, but when we're talking about mobile phones, there are several millions of mobile phones in the wild, right? So if you think that you can just have a server that is gonna have all the mobile phones connecting to the server at the same time, you're likely gonna DDoS yourself, right? And another thing about FL frameworks is that they are very, very early they're still in their early infancy. So things like the server tend to not really be that much scalable. They are vertically scalable in the sense that you need to throw more CPU resources, more RAM. You need to scale the machine up in order to scale for multiple devices. Of course, there are many things that you could do that there. I'm not going to go into too many details, but from scaling reads through replicas, or for writes, you could potentially have cohorts of devices and then have some transfer learning across these cohorts of devices. There is a lot of research already in that area. So yeah, everything goes on fire if you have these many connections. Fortunately, as we've discussed before as well, not all of these devices will connect at the same time, right? So some of these devices might be offline, they might be idle because the phone screen went off. You can also have policies to further reduce the number of devices that connect to your server. Things like you might decide that you don't want to waste power or reduce the battery lifetime on the user's devices. Thus, you only allow devices that are connected to power to initiate communication to the server and participate in the sampling rounds. You can enforce things like what you would see, for example, in Wi-Fi with retrials. You can have the devices only communicate back to you at random intervals of time, or you can even have more advanced techniques in which you kind of try to see like what's your load and use this information in order to decide when devices should be connecting to you and kind of play with this information. Finally, on top of the remaining devices, you can perform sampling just like what you would do in simulation as well. So how to achieve faster convergence in these scenarios? So you will see that there are many ways that a device can become a straggler, from communication level because of latency, because of limited bandwidth to compute. So in terms of latency, some devices might be connected with 5G and they have 1 millisecond of time just to reach the antenna of the ISP. You can have 4G connections with 40 milliseconds, and these 40 milliseconds it's the best case scenario, right? Because it can often, if you are if you go under a building or something like this, you can go to the entrance easily. 3G with 60 milliseconds, or you can even have like unreliable connectivity, and you have consistent disconnections and so on. But the thing here that is interesting is that like 40 milliseconds, it's actually slower than the time it takes to make inference with the mobile net model on a Samsung S9. So you can see that latency plays a very important role when doing federated learning on mobile devices. And you could say that if you want to converge faster, or to make your federated learning converge faster, you can understand quickly that if you have devices that are very slow, right, your conversions will take much longer as well. And typically in a round, your round will take as long as the slowest device takes to execute and communicate back the results to you, right? So one way that you could tackle this straggler problem would be, for example, in the basic scenario, you typically run only a single step or iteration on the mobile phone. But if you decide that you want to run more local iterations, then you can understand that now you're going 5 times through the data. So you don't have to communicate so much. You are doing more computation locally on the device before you communicate back and forward the weights. So this kind of saves a bit the communication and might help you achieve faster conversions. Now, the problem with this, and all of these solutions kind of have a reverse coin, is that if you do too many iterations locally, you also are increasing the chances of client drift, in the sense that you will have the clients, all of them going into a different direction, and when you try to aggregate, you might run into problems. In terms of compute stragglers, it's easy to understand as well that there will be devices in the wild that have very low compute capabilities all the way to high-tier devices, right? So how do you go in this case into making sure that your rounds are not lagging too much behind because of very slow devices? One could think of implementing timeouts, for example, in the sense that if a mobile device doesn't reply to you within a certain timeout, then you simply discard the results and conclude the round with the clients that already responded. But then it becomes also very hard to predict what timeout you should be setting, because depending on the demographics as well, you'll have very different network conditions. You will have very different mobile device distribution, for example. In the IoT world, this might become even more challenging. So typically, a decent rule of thumb is to pick just a percentage of your sample size, basically. So you say that 10% of the devices that might be slower, you just discard them, and this kind of works a little bit better, but it doesn't really solve the problem, let's say. Another thing that you need to keep in mind is that if you start discriminating your devices based on latency or based on their network conditions, and if you discard too many of these files, right, of these devices, you can start to introduce biases, because if low-tier devices don't participate in training, you might be discarding all the people that basically don't have money to invest on high-tier devices, for example. So you might be removing completely some demographics. Another thing is that sometimes it's very hard to predict during training if your model is actually generalizing well. Typically, you resort to inference in order to do this, because it's orders of magnitude faster. Finally, when it comes to bandwidth, it's a bit easier to tackle than, let's say, for example, latency. And here we've seen many works that do quantization of the data before transmitting it. When you quantize the data, typically your data becomes more sparse. Then you can use speed shuffling to kind of put all the zeros together. LZ4 on top of this for compression. And we've seen in this paper in text 21 that you see huge compression ratios of like 60 times smaller sizes. Now, with quantization, we also need to be very careful, because if you quantize your data, it will most likely affect your convergence as well and the performance of your training. So typically, you should try to go first for like smaller reductions in precision. For example, from 32 bits to 16 bits, maybe it's still acceptable and might not affect that much your performance. So yeah, finally, to leave some concluding remarks. We've seen that there is a lot of machine learning orchestration tools out there. They're becoming extremely widespread, but the federated learning frameworks are still in their early infancy. Scaling federated learning is hard. We didn't go into research papers here. We were more like on a practical kind of guide for you to get your hands dirty at the first stage. But the main takeaway here is that there is no single configuration that suits all the scenarios. Okay, it's quite challenging to have something that will work across all the possible use cases that you might think of. Therefore, we need smarter scheduling policies that adapt to dynamic environments. And here we're saying network conditions, resource contention, heat, battery capacity, and so on. Then also, we've seen that many of these scaling techniques often come at the cost of introducing biases. And finally, we need production-ready techniques that allow fair participation or proper representation of the discriminated devices. So here, many techniques like trying to reduce the resource requirements of the model of the models, things like order dropout or things like these that actually allow low-tier devices to participate in training as well, for example. So yeah, this concludes my talk. So if anyone has questions, feel free to ask.